In this work, we present a fast gate planner for acyclic legged locomotion named ContactNet. We discretized the possible footholds and ranked them offline with a novel cost function that considers tracking performance, stability, and robustness. In this way, we trained a multi-output regression neural network.
The network ranks the footholds in a few milliseconds. The approach is fast also for flat terrain with holes, since it discards a solution which are not current with the terrain, depicted by the yellow disks, choosing the best visible one, depicted by the blue disk. We integrated ContactNet into an MPC architecture. At every touchdown, the network computes a contact sequence used as a parameter by our trajectory optimizer. A centroidal and an impedance controller compute torques to execute the motion on the 2.2 kg Solo 12 quadruped robot in simulation. In the first simulation, we show the stability and accuracy of the ContactNet in a long horizon trot motion. We change reference velocities every 10 seconds, choosing random values in the range -0.1, 0.1 meter per second. Since the network has been trained with random robot configuration and random velocities, the robot reacts to the change of the velocities, modifying online the gate sequence and avoiding the holes in the terrain. Walk motion is demonstrated in the second simulation in presence of a complex scenarios with the stepping stones composed of circles, non-convex stars, and rectangles. The robot traverses the terrain with a completely acyclic gate. The planner is still online since the average computation time required to obtain the entire gate sequence composed of 3 consecutive actions is 1.6 milliseconds. In the third simulation, we traverse a terrain with 3 narrow and unevenly spaced stepping stones using a walk motion. We compare ContactNet with a foothold adaptation planner with fixed gate sequence. The latter fails, while our approach accomplished the task by changing online the gate sequence. We test the robustness of the ContactNet pushing the robot for 1 second. While being pushed, the contact planner adjusts gate and footholds to contract external disturbance and avoid holes. Finally, we evaluate the success rate of our algorithm for both walk and trot motion. We repeat 100 iterations each, removing randomly n patches of the terrain. The ContactNet has a success rate of around 95% for the walk and a smaller value for the trot due to its intrinsic instability. For n equal 110, the success rate of the walk motion is 93%, while using a fixed sequence, it reduces to 85%. In stark contrast with the other contact planning algorithm, the solve time is not affected by the complexity of the terrain.